So, we continue with our discussion on built-in self-test. In our last lecture, we talked about how we can generate the test patterns inside the chip. Now, in this second part of the lecture, built-in self-test, we shall be talking about the so called response compaction part. So, if you look into this picture, we have already seen how using LFSR you can generate the test patterns, the so called pseudo random test patterns. Now, let us say we are applying 10 to the power 4 or 10,000 such patterns. So, at the output of this circuit we will be getting 10,000 circuit output responses. What do we do with these responses? How do you take a decision whether this is good or bad? This is the question we are trying to answer now. Okay? Let us see. The first thing to note is that we require to do something called a compaction operation. Why is it required? Let us take an example, just like I was saying, that the circuit output can generate huge volume of data. Suppose a realistic figure, we are applying 5 million random patterns. The circuit can have 200 outputs, which is pretty common in modern day circuits. So, how many bits of data is generated? Number of test patterns multiplied by number of outputs. So, it will be 5 million multiplied by 200. This translates to 1 billion bits. So, what do we do? Do we store all these 1 billion bits in memory, and for every pattern the output generated we compare it? This means we require a 1 gigabit size memory just to store the circuit responses. Well, obviously, this is impractical, right? So, we have to do something else. So, it is really uneconomical or impractical to store all these responses on chip. So, we have to do some kind of compaction before we compare the circuit responses. Okay. This motivates us, why do we need compaction. Now, the point to notice that we have huge volumes of data. Okay, we said the circuit is generating huge volume of data. Then we have a compacting operation, let us say C. The compaction operation takes this huge volume of data and generates a small compacted response. And this small compact response is referred to as the signature. So, what we store in a ROM, because this signature is relatively much smaller in size, you can store this golden signature, that means the signature in the absence of any faults. So, through fault simulation you can do this experiment beforehand, you calculate the good signature, you store it in a ROM, and you can compare this signature with the signature stored in a ROM, whether they are equal or not, right. But you see, here we are having a many to one mapping. A huge set of data is being compacted into a very small signature. Typically, let us say the signature can be as small as 32 bits. So, there is always the possibility that 2 or more input patterns in this set can map to the same signature, because of which some of the faults might go undetected. So, what do we do? What is the probability of that a fault is occurring, but it is going undetected? Let us try to make a simple calculation. But before that, let us talk about a few terminologies. There is something called aliasing. Well, aliasing said just the point I have made, that there is a fault, but the faulty signature by accident becomes the same as the good signature. Okay. the signature in the presence of the fault matches with the golden signature, and under such condition fault goes undetected. We say that a aliasing has taken place. Well, to reduce the size of data, we broadly use two techniques. One is called compaction, other is called other is called compression. Now, in computers sometimes we compress files. There are commands like tar, zip, rar, many commands are there. They are used to reduce the size of a file, but this is a temporary process. Whenever we need the file again, we can unzip it, we can expand the file again and get back the original. So, this compression is a reversible process. You can do compression, you can again uncompress it. Okay? Reduces number of bits, but there is no information loss, it is fully invertible. But in compaction you cannot go back. You can drastically reduce the number of bits, like you can have a huge 1 gigabit data, you can bring it down to as low as 32, let us say, but there is some loss of information. From this 32 bit you cannot go back to the original 10 to the power 9. This you need to remember. Now, in circuit testing in BIST we go for compaction, we do not go for compression. Okay. Now, broadly speaking, this compaction or compression can be done in two ways. One, using something called signature analyzer, which can compress a single serial bit stream. That means, assuming the circuit has a single output. So, single bit stream is coming, and second alternative is something called multi input signature register, where this circuit can have multiple outputs. So, we can compress all of them together. Okay. Let us see how. First, let us talk about signature analyzer, how it works. We can use an LFSR again here, linear feedback shift register again, to use as a response compactor. The same technique is used for error detection using cyclic redundancy code check. The basic mathematical foundation is that we are dividing a polynomial by another polynomial and take the remainder. This remainder is what we are calling as the signature. Mathematically this is the basic concept, but how it is implemented, let us see. You see, the circuit output is generating some data. Okay? We are applying input patterns one by one. In the output, bits are generated. Now, these bits are treated as coefficients of a polynomial in decreasing order. So, we will take an example, and we have a compaction circuit based on LFSR. What the compaction circuit will be doing? It will be dividing this polynomial representing the output bit stream by the characteristic polynomial of the LFSR. So, LFSR we have seen that there is a characteristic polynomial. So, polynomial division will take place, and whatever remainder will be there in the LFSR, that will be the signature. And one thing to remember, before testing starts, we must initialize the LFSR to the all 0 pattern. Okay? Fine. Let us see how it works. Let us take an example. This is a 5 bit LFSR which implements a polynomial like this, x to the power 5, x 3, x and 1. So, the feedback are coming like this, x to the power 5, x 4, x, then x for x cube, there is a feedback from x cube, then x, then well, you can actually call them in a different way in terms of the polynomial. These are the outputs, but in terms of the coefficient of the polynomial, you can call it x to the power 5, you can call this x to the power 4, you can call this x to the power 3, x square, x, and this is x to the power 0 or 1. So, feedback is taken from x to the power 5, x to the power 3 and x, you see these terms are there, and we have used a type 2 LFSR, where the XOR gates are in between the D flip flops, right, and the circuit is generating an input bit stream, say 01, 01, 0001. Okay. So, the input polynomial, you see, if you consider the output side 0, 1, 2, 3, 4, 5, 6, 7. So, this will be x to the power 7, 7, 6, 5, 4, 3, x to the power 3, 2, 1. That is why x to the power 7, x 3 plus x. So, any bit pattern can be represented by a polynomial. So, your input polynomial is this, your characteristic polynomial of the LFSR is this. So, I am saying that there will be a division of this polynomial by the characteristic polynomial. This will happen automatically. And here if you just work it out and take the remainder, remainder comes to x cube plus x square plus 1, which in terms of bit pattern x cube, x square, no x and 1, 1 1 0 1. This should be the remainder, right. Now, if we just work out, just initialize it with all 0 pattern, simulating the process of division, the input bits are coming like this, and if you work out, I leave it an exercise for you, you leave it, you just see it step by step. This corresponds to the input polynomial, and as this input bits are coming one by one, the LFSR runs starting from the all 0 state, you will see that the end whatever remains, this is nothing but this 1 1 0 1, you see this is this polynomial, I said x cube plus x square plus 1. Final value in the LFSR whatever it remains, this will be the remainder polynomial. This is how polynomial division takes place or works. Okay. So, you need not have to know much more detail about this, just remember that it works. Talking about the probability of aliasing, that what is the chance that some error will occur, but we will not be able to test it. Let us see. Suppose the number of bits in the input stream is m and LFSR is an n bit LFSR. So, in the input we have an m bit string, which naturally will be having 2 to the power m combinations, and finally, in the LFSR we are compressing it to an n bit stream. So, there can be 2 to the power n possible signatures, and out of this 2 to the power n, one of the signature will be good, and out of this 2 to the power, you see there is 2 to the power m input combinations, okay, in m bit, but out of them one of them is good. Similarly, in the output signature there can be 2 to the power n possible signature, out of them one of them is good. So, there are 2 to the power m minus 1 faulty input strings and 2 to the power n minus 1 faulty signatures. Okay. Now, assuming that the input patterns, this is a much larger set, are uniformly distributed among the signature. So, how many input patterns will map to each signature? 2 to the power m divided by 2 to the power n, which comes to 2 to the power m minus n. 2 to the power m minus n patterns map to a particular signature in the LFSR. Just remember this. So, probability of aliasing I mentioned, it is defined as the ratio of the number of faulty bit streams, it is a probability. So, number of faulty bit streams that map to the golden signature to the number of total faulty signature. now we have said already seen that 2 to the power m minus n input patterns can map to every signature, and one of them will be the golden signature. So, 2 to the power m minus n input patterns will map to the golden signature, and out of this 2 to the power m minus n, one of them will be the good one. So, 2 to the power m minus n minus 1 will be faulty bit streams that map to the golden signature, and these will lead to aliasing. So, probability of aliasing will be this number of cases divided by total number of cases. Total number of faulty bits 2 to the power m, out of them 1 is good, 2 to the power m minus 1. So, if m is very large, so this approximates to 1 by 2 to the power n. And you see, even if you choose n equal to 32, this is independent of m. 1 by 2 to the power 32 is so small, the probability is something into 10 to the power minus 10. So, well, yes, there can be aliasing, but the probability of aliasing is very small. Because of this, people do use this technique, and a signature of size 32 or 64 is considered to be good enough. All right. Okay. Now, talking about multiple input signature register, let us briefly talk about it without going into the detail, because a circuit in general can have multiple outputs. Okay. So, when you apply a sequence of test patterns, bits will be generated from all of these outputs in a stream, right. So, suppose if we use an LFSR based compressor with every output bit, then this will require too much hardware, lot of hardware. If there are 100 outputs, you will be needing 100 LFSRs. Okay. The solution is to use multiple input signature register, which is called MISR in short, where you are using a single LFSR. How I will show you. So, you did not have to remember all these details, because LFSR is linear, you can compress all the output bit streams in a single LFSR. The final response will remain something like same as if you XOR these responses, and the final response you will get, they will be same. Okay, let us see how it works, how this circuit will look like. Well, an MISR looks like this. You see, this is a type 2 LFSR, where not only I am feeding data in the first XOR, but I am adding an additional input to all other XORs. So, even in the places where there is no feedback or tapping connection, I am adding an XOR gate. So, that for this circuit, so all the outputs can be fed in parallel to all these XOR gate inputs. So, all the bit patterns, suppose out here I am applying 10 to the power 6 patterns, 1,000,000 patterns I am applying. So, each of the circuit outputs will be generating 1,000,000 bit streams, they will all be compacted together, and finally, a single signature will remain stored in the register at the end, right. This is how this circuit works. So, to summarize here, if you talk about built-in self-test, the preferred method, as I told, is that you use pattern generation using LFSR based pseudo-random patterns, and on the output side you do compaction using multiple input signature register. But you understand, BIST has a lot of overheads, you need to have this pattern generator, response compactor, the ROM to store the golden signature, the comparator. This additional hardware also has to go inside the chip. Okay. These are the additional overheads, and they also lead to performance degradation, because now the primary inputs that you are feeding to the circuit, that has to go through a multiplexer. The multiplexer will be having some delay, so the delay of your circuit increases. So, some degradation in performance also occurs. But the advantages of BISTs are pretty significant. Test cost gets reduced drastically. You are able to do field testing and diagnose which chip is good or bad, and you can test the circuits at its full speed. These are some of the very big advantages. So, with this we come to the end of this lecture and also this course. So, over the last 12 weeks we have covered many of the topics. Most of the topics are conventional in the sense that you will find them as part of standard curriculum in most of the courses in switching circuits or digital circuits. But I have also tried to cover a few topics which are a little unconventional, which are a little off the track, which are normally not a part of the syllabus, but I just wanted to give you a flavor of some of the techniques or technologies which have possibly greater impact that you can see in the future. So, with this and wishing you all the best, let me say goodbye to you. Thank you very much.